Hello teachers, welcome to Chapter 2, Section 2-1, and this is Part 2. Let's talk about what we talked about in Part 1, just in case you're jumping in. Quantifiers and their effects on statements. Remember, we talked about existential quantifiers and universal quantifiers, so we covered that. Different forms of statements, we covered that. Okay, how to determine whether two statements are logically equivalent. We actually haven't gotten there yet. How to develop logical arguments. We haven't gotten there yet. And how to determine whether an argument is valid. So it looks like we have a whole lot more to go. We really don't, because we spent a lot of time talking about different forms of statements and compound statements, with the conjunction, which is an and, a disjunction, which is an or, and a conditional, which is an if-then. Now, we're just jumping right into a truth table. They don't waste any time building up to this stuff. And so we're trying to prove that this statement is true. Now, let's read it in the symbols in the proper language. So you could read this as if P, then Q, is equivalent to, y'all, whenever you see those triple lines, that's equivalent to not Q, or if not Q, then not P. Another way to read it is P implies Q is equivalent to not Q implies not P. Okay? All right. Now, they want us to prove this. So, to prove this using what we call a truth table, that's what this guy is right here, then we need to put every possibility on the top row. So, what am I saying? So, we need a column for P. We need a column for Q. So we've got that, okay. Look, there's a not Q that shows up in this statement. So we could go ahead and do a column for not Q and do a column for not P. Now you might be asking, why didn't you put not P before not Q? It doesn't really matter, y'all. The reason I put it in that order is because this is in this order right here. I'm going to make a column for P implies Q. I'm going to make a column for not Q implies not P. Okay. Now I'm going to flip on you. I'm going to flip the pages where this is all typed up. In fact is, it might not even be in the same order I just wrote that in. And that's to tell you that the order you put these up here in doesn't matter. Let's just see what the book wanted to do. Look, they did P and Q, and then they went ahead and did the if P then Q in the next column. Is that okay? Of course it is. Then a column for not Q, a column for not P, and then finally not Q implies not P. Now let's fill this in. You remember how in the last video I told you if you have statements P and Q, the smartest thing to do is take your number of rows. By the way, the book, to determine the number of rows, what you do is you do 2 raised to the number of statements. Okay? Now, when I mean statements, I mean like P's and Q's. So there's just a P and a Q. There's no R or S or T. So that would be 2 to the second. That means I need 4 rows. Now, we already had 4 rows established for us. I noticed in the homework they already established that kind of stuff for you. But if you were to build this just cold on your own, you would need to know that, right? So we need 4 rows. Now what you do is you take that number 4 and split it in half. And that would leave us with 2 trues and 2 falses. In the last video I said, trust me, it's 2 TTFF, true, true, false, false. And in the next column, you take the 2 and split it in half, which is 1, of course. And then you just do 1 true, 1 false, 1 true, 1 false. But if you're only dealing with simply P's and Q's and nothing else, this works the same way every time. True, true, false, false, true, false, true, false. Okay? Now, if P, then Q. Now, you might have to go back to the truth table for if P, then Q. You want to scroll back there and look at that? Let's do it. Here it is. Remember that the only time an if P then Q is false is when the Q is false. So true, true is true, false, true is true, and false, false is true. So if you start with a false, it's always true. If you start with a true, it also has to be then true. All right, so let's use that to fill in our table. Okay, so we're back at our table. Remember, true, true is always true. But if true, then false is the only situation that you have a false for a conditional statement. If false, then true. Remember, if you start with a false, it's true. If false, then false. Again, we're starting with a false. Okay, now we're moving on to calculating the negation. So not Q, what do? You just take the Q column and change the truth value. So true turns into false. The second false turns into a true. This third true turns into a false. This fourth false turns into a true. You with me? Just change all the Q's. Not P, or the negation of P, you change all the P's. So not true turns into false. Not true turns into false. I'm on the third row. Not false turns into true. Not false turns into true. Now, this says not Q implies not P. Now keep in mind, y'all, we're only looking at these two columns. Well, the highlighter's a little intense there. I'm only looking at these two columns. Okay? In that order, because it says not Q implies P. So a lot of times I have to draw lines. We're going from not Q to not P. False implies false. Remember what we decided that was? If you start an if-then with a false, it's true. If you start an if-then with a true, it depends on what's after that. True implies false is what? False, right? That's the only one that's false. If you start with a false, then it's true. And here's a true implies true, which is true. Okay, now I'm going to switch pages on you, and all this is typed up, but it's the same results, so just bear with me. Here are those typed up results. Now, how did we prove that P implies Q is equivalent to the statement not Q implies not P? Well, look at your columns, okay? So P implies Q. That's this column right here. Okay? Not Q implies not P is this column right here. And look at the truth value. They're identical, right? True is in the first row, false is in the second row on both, true is in the third row, true is in the fourth. And so that's how you prove that these are equivalent statements, is you can do a truth table, and if you get the same truth values for your true, 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 false, your P's and Q's, then you know they are equal to each other. So it's like substitution. You could use not Q implies not P in the place of P implies Q. But now what did we really do? Remember, this is the contrapositive. I already let you know that the contrapositive is identical to the original if P then Q statement. So we just proved it. And we didn't have to talk about San Francisco being in California to really do it. Now I've got another truth table for you. Not only that, it defines something called a biconditional. Notice the notation here. So a biconditional is the double arrow. Now really what it is, the definition of it is right over here in the last column of your truth table. It means if P then Q and if Q then P. And it's read P if and only if Q. But it really means P implies Q and Q implies P, both directions. Okay, so let's do our setup like we've done in the past, right? So my P column is true, true, false, false. My Q column is true, false, true, false. Now again, why am I doing it like that? Because I need every possibility of true and false that could happen with two different statements. And this just keeps it organized if you do it in that order every time. Now let's do the if P implies Q column. Remember, P implies Q. The only time it's false is when you have a true then a false. So that second row is false. All the other ones are true. True implies true is true. False implies true is true. False implies false is true. If you start a conditional with a false, it's true, no matter what. Okay? Now we're going Q implies P. Now careful here. you got to read these things backwards. Okay, so if it starts with a Q implies P, so I'm going backwards. I'm saying true implies true is true. Starting with a false here, right? Right here. False implies true. That's true. True implies false. Remember, that's the only time it's false. If you start with a true but end with a false, it's false. False implies false is true because I started with a false. All right. Now an and statement. Remember, we did ands in the last video in part 1. So when we do an and statement, I'm desperately searching for colors, stand by. Okay. So when we do an and statement, the only time an and is true is when they're both true. And what columns am I looking at? I'm only looking at the P implies Q column, so this column, and the Q implies P column, so this column. And I'm even going to erase my little arrow here because I've already handled that. It's like scratch work. We don't need it anymore. Okay, so and between them, true and true, remember, is always true. But if you have a false and true together, that's false, right? True and false, no, that's false. True and true, aha, we got a true again. Okay, so this is the biconditional statement. If you had to memorize the biconditional statement, it would be this. That you notice the pattern? I'm looking at just P's and Q's now. The pattern is if they match. So true, true is true for a biconditional, and false, false is true for a biconditional. But if either one of them is false, then your answer is false for a biconditional. And then the next page is all typed up and fancy for you. So again, a biconditional, be careful, look for those double arrows, and it is read P if and only if Q. And really just, it means you read P implies Q and Q implies P. And we've done a truth table for it. Okay, we're getting there. Not much more to go. Valid reasoning. What in the world does that mean? It says, if the conclusion follows unavoidably from true hypothesis. So what you'll be given is something actually called an argument. And you will have hypothesis, probably more than one, and a conclusion. And you could say the argument is valid as long as if the hypothesis is true, then the conclusion is true. Now, I want to make this clear. The hypothesis does not have to be true to have a valid argument. We're only saying that if the hypothesis was true, and that makes the conclusion inevitably true, then you have a valid argument. So that idea gets confusing. You can have a false argument, let me say it that way, but it still be valid, okay, because your hypothesis don't have to be true. Now, let's look at an example. I think this will clear some of that up for you. Okay, all cats like fish. That's a hypothesis. We don't really know that. I'm pretty sure there's a picky cat on the planet, or 80, that don't like fish, right? But we're not worried about that. We're going to assume the hypothesis is all cats like fish. And then the next hypothesis is Felix is a cat. We don't have to test that out. There's probably a cat named Felix, but it doesn't even matter if there's a cat named Felix. All we're saying, if those two things are true, does it follow naturally that Felix likes fish? Okay, now you might have that argument built in your head and you can say, absolutely, that's a valid argument. But I got a technique for you that you might like, and it is called an Euler diagram. Okay, so E-U-L-E-R. That is a mathematician, very prolific mathematician. That really is read Euler. I know it looks like Euler, but it's read Euler. We can use an Euler diagram to represent the validity of this reasoning. So what is an Euler diagram? It's lots of circles, y'all. All right, so what you do is you draw circles to represent each hypothesis. Sometimes it's just a dot. Hang with me, okay? All cats like fish. Okay, so what you do is you draw a circle. Get my pen working again. You draw a circle to represent that all cats, this is my cat circle, like fish. Okay? Now, anytime you have an all statement, it means you have a circle inside another circle because all of these cats fit inside the like fish circle. Okay, now let's look at the second hypothesis. I'm going to change colors on you. Felix is a cat. Now, where do I put Felix? You can have your own circle for Felix, but Felix is just one cat, so I'm just going to put him right here in the cats. Does that make sense? Of course, because it said Felix is a cat. Now, y'all looking at your picture, can you tell that Felix likes fish? I say you can, right? Because Felix fits inside the likes fish circle, right? And this means, just from a diagram, this is a valid argument. Now, is it a true argument? What if Felix is one of those cats that doesn't like fish? You know, there's 80 of them or something, right? It doesn't matter. All we're saying is if it's true that all cats like fish, and it's true that Felix is a cat, because this is a valid argument, it is also true that Felix likes fish. Okay, so that's why it's valid. It doesn't have to do with it's true. Valid means if your hypothesis is true, then your conclusion is true. I hope that was clear. And here's the book's version of this. Looks like mine, right? So we can use an Euler diagram to represent the validity of this reasoning by saying all cats like fish. So the cat circle fits inside the fish circle. And then Felix is a cat, so boom, we put him right in the middle of the cat circle or even on the edge, it doesn't matter. But we don't put him outside because he's a cat. And then you could look at the picture and tell, because our Felix dot fits inside the likes fish dot, this is a valid argument. So let me make it clear one more time. Valid. Right? Okay, I think I've got one more of these for you, then we can shut this one down. We do. This is my last argument. Valid argument here. Maybe not valid argument. We're going to try to figure it out. It's slightly more complicated than the last one, so we're going to do our best to draw a picture. It says, determine if the following argument is valid. So we've got two hypotheses. The first one, it says, in Washington, D.C., all lobbyists have influence. So we've got to draw a picture for that. Think we can do it? Because I'm lacking space here, I'm going to go to a blank page. But picture it in your mind. In Washington, D.C., so we could do a circle for being inside Washington, D.C. All lobbyists, hey, we got that all thing going on again. Anytime you have an all, you need a circle inside another circle. Have influence. So, next page, here we go. Get my color straight. Okay, so let's do a big old giant circle. This is Washington, D.C., right? Remember what it said? All lobbyists have influence. Now, you've got to decide which one fits in which one. It says all the lobbyists have influence. So, lobbyists is actually my smaller circle. I'm just going to put lobbyists, okay? And then it fits inside the influence circle, which also fits inside the DC, because that's all we're talking about. We didn't really have to have the DC circle, but it made me feel a little bit better, so I put it there. Now let's go back to our hypothesis. So in Washington, D.C., all the lobbyists have influence. Let's look at it again. I'm in Washington, D.C. All the lobbyists fit inside the influence circle. Does that mean that only lobbyists have influence? Nope. Okay. Now let's look at the next hypothesis. And I'm going to use my pen and change it to some other fancy color. Okay. No one in Washington, D.C. over 6 feet tall has influence. So we're still inside Washington, D.C. Good news. It says no one over 6 feet tall has influence. So I need to put these people over 6 feet tall somewhere. And you know what I do? I don't put them in the influence circle. Okay, so that really means that I need a different circle. Okay, I can't put them in the influence circle. So these are my 6 feet tall people. They're still in DC, but they're not in the influence circle because it says no one over 6 feet tall has influence. Now, what's my conclusion? We've got to use this picture to determine if my conclusion is right. Okay, it says persons over 6 feet tall are not lobbyists in Washington, D.C. What do we think? Let's look at our picture. Persons over 6 feet tall, do they fit inside the lobbyist circle? Nope. So I would say this is not valid. Definitely not valid. Okay. Now, I'll tell you, the book did it a different way, and I'm going to show it to you, and I'm not a fan, but I'm going to show it to you anyway. Okay, so here we go. It says we can use Euler diagram to represent the validity of the reasoning. Now, here's their reasoning. All right, they're saying that the L is the lobby, and the I is the influence. Okay, then they moved on to B. Not really sure why they did an A and a B here. But lobbyists, this is the second hypothesis. I think that's what they're trying to say. You still have lobbyists, you have influence, but there's our 6 feet tall people. Okay, and they label it. But from this, you could still tell the same thing that we could tell in the other one, that our 6 feet tall people, they call that W, do not fit inside the lobbyist group. They are not in there. So again, this is a... What did we decide? Persons over 6 feet tall are not lobbyists. Yes, is a valid argument. Y'all had to go back and research just to make sure I was arguing that right. But this is definitely a valid argument because the conclusion is that these folks that are 6 feet tall or over are not lobbyists. Now, is that true? Well, no. I mean, there's probably plenty of lobbyists that are 6 feet tall that actually have influence. Is it even true that all lobbyists have influence? Probably not, right? So, things to keep in mind. But a valid argument means if the hypothesis is true, all of them, then the conclusion must be true due to the hypothesis. That makes it valid. And there are plenty of invalid arguments. And so then it breaks down where that doesn't fit in. Okay? Oh, look, back up. I said it wasn't valid. Persons over 6 feet tall are not lobbyists. Okay, actually, my bad. And I didn't mean to contradict myself. I'm so sorry. I don't mean to confuse you. It's valid. What I ignored when I said it was not valid, it said persons over 6 feet tall are not lobbyists. Y'all are not lobbyists. And my circle completely shows that the 6 feet tall people did not fit inside the lobbyist people. So this is valid, which does match what we have over here too. As you can imagine, these diagrams get confusing. And there's not only one way to do it. I liked my way better than the book way, but I would, right? So you do what you have to do to get the job done. If you've got lots of questions about this, please let me know. I always want to be accessible to you and help you out in every way I can. I hope you have a wonderful day.